All right, hello everyone. This is Andrew Adams back at it. And today we got a runtime analysis problem here. So it's pretty simple. We got two for loops and something atomic inside the second for loop. So let's go ahead and write it out. We always start out with changing the for loops to summations. So there's two for loops, two summations. And there we go. So we'll do two of these. The one on the left is the first one. So we do I equals 1 to n minus 1, and then the inner loop, the bounds are from j equals I to n, and then here it says do something atomic. Whenever we see that, we can just put a plain old 1 right there. So I think that's part's pretty simple and self-explanatory. Then let's go ahead and deal with this first one here. We always want to work from the right to the left when we do these kind of problems. So we'll start here on the right. Now we're doing constant from j equals I to n. Whenever we see that, we know our bounds are from I to n. So we can just use the formula, the second bound n minus the first bound I plus 1. And one thing that I got tripped up on initially was why there's this plus 1 here. And the reason for that is, say we're going from 3 to 5. So we have 3, 4, 5 right here. If we just did 5 minus 3, that would equal 2. But we can see here there's obviously not two values, there's 3. And that's why you add the plus 1, because when you do these bounds, there's always an extra 1 in there. So let's get rid of those now. And then we just have to deal with this outer summation. So we have I equals 1 to n minus 1. And to solve this, it'll be easier if we go ahead and split this out into individual summations. So we'll have I equals 1 to n minus 1 of n minus I equals 1 to n minus 1 of I plus I equals 1 to n minus 1 still of just 1. And all we did there was we split up the summation. So first, there's some tricks here to know. The main ones are, if you see an n, you can just multiply that by the second one up here. And then if you see an I, there's special formulas you need to know. So first, for this n thing, like I just said, you can multiply the n minus 1 by n. And the reason for that is whatever n is, we're doing that n minus 1 times. So we're doing n times n times n times n, and we do that from 1 to n minus 1. So since we're doing that n minus 1 times, we can just do n times n minus 1. Then we got to subtract this out here. This one has a special formula. When you're going from something to something and there's an I on the right, there's this formula you need to know, which is n plus 1 over 2. And what this n in here is whatever your second bound is. So instead of n, we're going to do n minus 1, n minus 1. So we'll make that a little cleaner down here. We're going to have n minus 1, and then n minus 1 plus 1 over 2. And there's theoretical ways to go about finding out these summations. I think it's easier for the purposes of just computer science, trying to get a basic theoretical knowledge, just to memorize these formulas because there's not that many of them. And then this is just constant right here. So whenever you have constant, you can use this formula we use back here, which is second bound, n minus 1, minus first bound, which is 1, and then plus 1. So we have a minus 1 and plus 1 that cancel out, so we can get rid of that. All right, then let's just do some simplification here. And we're going to get that all equals n squared minus n. And then the second part, this here cancels out. So we got minus n squared minus n over 2. And then the last part, plus n minus 1. got a minus n and plus n here, which we can get rid of. And then we can already see right here, once you get to this stage where it's all simplified out, all you want to do is you want to see basically what your highest order of n is. And we can see that it's going to be n squared. So then we can simply simplify by having our final answer be, what is our big O analysis here? It's going to be O of n squared. That will be our big O. So again, just to recap that, when we see n squared, there might be, when you get to the end of these problems, there might be a million n terms. There might be an n, there might be a log n. But because n squared is the highest order of all those, then that will be our final big O, and that will be our final answer. So I think this is a pretty straightforward example. Let me know if you have any questions or anything I can help out with. And thanks, guys, for watching.